In this video, we are going to talk about conditional GANs. And the motto for conditional GANs is generating images based on user choice. So now we are going to have more control over the image generation ability of the GANs. So let's see the features of C-GANs or conditional GANs. Why do we need them? First of all, currently we don't have any control over the generation. For example, all I'm doing is to give some random noise to the generator, and it's the choice of the generator whether he wants to convert it into a shoe or a bag or a t-shirt. So we don't have any control over the generation. So this leads to this statement: we want some control over the images that are to be generated. We don't want to randomly generate images. We want to generate very specific images which we need. That's why in 2014 a paper was published with the name Conditional Generative Adversarial Networks. So in this architecture, instead of just giving the random noise as an input to the generator, we are going to give the input labels as an input to the generator and discriminator as well. So those input label will determine or will tell the generator how you need to convert this random noise into the image. For example, if the labels are for sneakers, then the generator will convert that random noise into sneaker image. So this is going to give us control over its generation ability. Now let's talk about the architecture. So as you can guess, this time instead of just giving a random noise, we are going to give the labels as an input to the generator as well. So this orange represents my random noise, and this dark blue represents my input labels. And then we are going to give them to some layers that could be dense layers or convolutional layers. So in the original paper in 2014 they just use dense layers, but we are going to use convolutional layer because on images convolutional layer perform better than dense layers. So consider these dark circles like our convolutional layers, and finally it will generate an image. And in case of discriminator, the architecture will look very similar. We are going to give the labels as an input along with the image, and the discriminator is going to determine whether this image is real or fake. So in this case the objectives will be two: whether the image is real or fake, or whether the image matches the input labels or not. Now let's see the encoding label information techniques. In case of MNIST or fashion MNIST, the labels are just integer values like 0, 1, 2, 3, 4. So we need to encode that information somehow so that model could understand what does 0 mean, or what does 1 mean, or what does 9 mean. For this purpose, we have a couple of techniques. One of them is using one hot encoding and then a dense layer. So for example, on the right side you can see that I have one hot encode matrix for my labels. So the first row represents my labels 0, 1, 2, 3, 4, 5 up to 9, and in each column I have one hot encode vector. So for 0 label I have this vector, and then for 1 I have this vector. So here as you can see that each vector is unique, and this will help model to determine whether I need to convert this noise into sneaker or shoe or bag or shirt. But using this one hot encoding and dense layer is bit computationally intensive task. So there are some other better approaches to this problem as well, and one of them is using embedding layer. So if you are familiar with natural language processing in TensorFlow or even in PyTorch, you might be familiar with embedding layer. So what embedding layer does, we give some categorical value, some integer value to it, and it outputs a vector for us, similarly to this one hot vector. But in case of one hot, the vector is quite sparse, so you can see that we have a lot of zeros, But in case of embedding, the vector isn't that much sparse. So in embedding vector we have more information as compared to one hot encoding, and that's the reason why we need to pass this one hot vector to the dense layer, so that we could put some more information into this sparse vector, which makes things bit computationally intensive. So that's why in our case we are going to use this embedding layer instead of one hot encoding and then dense layer. Then we want to somehow include this encoding information into the input noise. So there are a couple of other methods which will let you include that label information into the noise. One method is to use this concatenation layer. So just concatenate the encoding information with the noise and give it as an input to the model. And another method is element wise multiplication. So instead of concatenating it, which will increase the input size, what we are going to do is to multiply our embedding layer information with the noise and then feed it to the model. So our size of the input will remain as it is, and it is not going to cost us in terms of compute power. The fifth approach is used in more advanced models, but yeah, I should discuss it as well. That instead of just giving this label information along with the noise to the starting layer of the generator or the discriminator, what we can do is to feed that encoding information into the intermediate layers as well, or especially it is recommended that you should insert this encoded label information to the last layers, so that the rest of the model could focus on converting the random noise into some meaningful image. Now let's see the generator code of the conditional GANs. So instead of just giving noise as an input, this time we are going to give label and noise as an input to the model. And first of all, we are going to pass that label into the embedding layer to get that encoded vector, and then we are going to use concatenation layer, and we are going to concatenate noise with the label. This is going to give us x, which we will pass to the dense layer, then reshape it, and upsampling, convolutional. So these are all the very standard DC GAN operations. So the new part is these about 3 lines. Now let's talk about the discriminator. So the discriminator code will look very similar to the generator. In terms of this embedding and reshaping, we are going to give label and image as an input, and we are going to pass that label to the embedding layer of the discriminator, which will give us the encoded vector, which we will reshape. So in case of discriminator, here you need to understand that the size of the image is going to be 28 by 28, and if this label is a vector, for example 100 rows vector, then we cannot directly concatenate those 100 rows with the image, because image is two-dimensional and our vector is single dimensional. So we need to reshape that vector into two-dimensional matrix, and we need to do it in such a way that the final output should be 28 by 28, so that we could concatenate it with 28 by 28 image. So that's why in case of discriminator, the output embedding shape for the embedding layer will be 28 by 28, so that if we provide an integer value, it should return us 786 rows vector, which we can easily reshape to 28 by 28. So the output embedding shape of this embedding layer will be 768, and then the reshape layer is going to reshape that 768 to 28 by 28, which is actually divisible. If you multiply 28 by 28, you will get 768, and then we are going to concatenate those labels with the image. So this x have two channel dimensions, one for the actual image and one for the encoded labels. And then we are going to pass x to the convolutional layer, batch norm, leaky value, and rest will remain as it is. So I hope you have understood this code. If you still have confusions, don't worry, in the next video we are going to write the code, and I'll see you there. Bye bye.